Welcome to this detailed exploration of Pico-Injection and Droplet fusion, two powerful techniques that enable precise reagent addition in droplet microfluidics. These methods allow us to perform sophisticated, multi-step reactions in flowing systems. Before we dive into the details, let's understand why we need these techniques in the first place. Many chemical and biological reactions require multiple steps. You can't just mix everything at once, because the timing and sequence matter. You need to add reagents at specific points during the reaction. In droplet microfluidics, each droplet is an isolated compartment. Once formed, it's sealed by the surrounding oil phase. So how do you add something to a droplet that's already moving through your device? This is where Pico-Injection and Droplet fusion come in. They provide controlled, precise methods to add reagents to existing droplets during their journey through the microfluidic channels. Let's start with Pico-Injection. The name itself tells you something important. We're working at the picoliter scale, which is extremely small. Here's the basic setup for Pico-Injection. Droplets flow through a main channel. At a specific location, there's a perpendicular injection channel with a tiny nozzle. This nozzle can inject precise volumes of reagent directly into passing droplets. So how does Pico-Injection actually work? What's the physical mechanism? Let me explain the key principles. Pico-Injection relies on pressure-driven flow. A reagent reservoir is connected to the injection channel. By applying a controlled pressure pulse, you can force a small volume of liquid through the narrow injection orifice. Timing is critical. The pressure pulse must be synchronized with the arrival of each droplet. Modern systems use optical detection to sense when a droplet is at the injection point, then trigger the injection. The flow rate through the injection channel follows the Hagen-Poiseuille equation. Q equals pi times radius to the fourth power times the pressure difference, divided by 8 times viscosity times length. Notice that radius appears to the fourth power. This means the injection channel diameter has an enormous effect on flow rate. If you double the radius, flow increases by a factor of 16. This gives you precise control through channel geometry. Let's do a quick calculation to understand the volumes we're dealing with. How much reagent actually gets injected? A typical droplet might be 50 micrometers in diameter. A typical injection volume is around 10 femtoliters. Let's calculate what fraction of the droplet this represents. The droplet volume is 4/3 pi r cubed. With a radius of 25 micrometers, we calculate the volume. This gives us approximately 65 picoliters for the droplet volume. The injection fraction is 10 femtoliters divided by 65 picoliters, which is 10 times 10 to the negative 15 divided by 65 times 10 to the negative 12. This gives us about 0.015%, or roughly 1 part in 6,500. That's an incredibly small but precisely controlled addition. You might wonder, why work with such tiny injection volumes? Why not inject more reagent to make a bigger impact? The answer relates to droplet stability. If you inject too much volume too quickly, you can disrupt the droplet interface and cause it to break apart. Small injections maintain the integrity of the droplet while still adding sufficient reagent. Also, for many biological applications like single-cell analysis or enzyme assays, you need precise concentration control. These small injection volumes allow you to fine-tune reagent concentrations with extreme accuracy. Here's what happens during Pico-Injection. The original droplet flows past the injection point. A small volume containing the reagent is injected, creating a temporary inhomogeneity. Rapid mixing inside the droplet then homogenizes the reagent throughout the volume. Now let's move on to droplet fusion, which is conceptually different from Pico-Injection, but serves a similar purpose of adding reagents to existing droplets. In droplet fusion, instead of injecting through a nozzle, you create two separate streams of droplets. One contains your sample, the other contains your reagent. Then you bring these droplets together and merge them into single combined droplets. Here's a typical fusion setup. Two parallel channels bring sample droplets and reagent droplets to a fusion chamber. In this chamber, pairs of droplets meet and coalesce into single larger droplets containing both components. So how do you actually make two droplets merge? Droplets are naturally stable. They don't spontaneously fuse. You need to provide energy or change conditions to overcome the interfacial energy barrier. The first method is electrocoalescence. You apply an electric field across the fusion chamber. This field polarizes the droplets and creates attractive forces between them. It also thins the oil film separating the droplets, allowing them to merge. The electric field strength is voltage divided by distance. Typical values are a few kilovolts per meter. The force on the droplets is proportional to permittivity times radius cubed times electric field squared. This shows that larger droplets experience stronger forces, which helps ensure reliable fusion. The second method is passive fusion using clever channel geometry. You design the channels so droplets are forced close together and squeezed. The mechanical pressure thins the separating oil layer until the droplets touch and merge. A third approach involves carefully controlling surfactants in the oil phase. By locally changing surfactant concentration or using photoactivatable surfactants, you can destabilize the interface exactly where you want fusion to occur. Now let's compare these two techniques. When would you use Pico-Injection versus Droplet fusion? What are the trade-offs? Pico-Injection has several advantages. You only need to generate one stream of droplets initially. This simplifies the setup. Also, you can inject at any time point, giving you flexibility in reaction timing. However, Pico-Injection requires precise timing and fast valves or pressure controllers. The injection nozzles are very small and can clog if your reagents contain particles or precipitates. Droplet fusion can be advantageous because it can work passively with no moving parts or electronics. This makes it robust and simple to operate. It's less prone to clogging issues. The challenge with fusion is that you need to generate and synchronize two droplet streams. If the droplet production rates don't match perfectly, you get pairing errors where droplets miss their partners. Let's calculate what level of precision you need for droplet pairing in fusion experiments. This will show you why synchronization is such a critical challenge. Let's say your droplets are spaced 100 micrometers apart and they're flowing at 1 centimeter per second. What timing precision do you need? The time between droplets is spacing divided by velocity. That's 100 micrometers divided by 1 centimeter per second, which equals 10 milliseconds. For reliable pairing, you need the droplet generation in both channels to be synchronized to better than about 1 millisecond. This requires very stable flow control and carefully matched channel resistances. Now let's discuss why these techniques are so powerful. They enable multi-step reactions in flow, which opens up entirely new experimental possibilities. Here's an example workflow. Sample droplets enter the system. First injection adds an enzyme. An incubation channel provides reaction time. Second injection adds a detection reagent. Finally, fluorescence is measured. This entire multi-step protocol happens in a continuous flow system. Let me give you a concrete example. Suppose you want to measure enzyme kinetics for thousands of different enzyme variants. Multi-step droplet microfluidics is perfect for this. First, you encapsulate single cells, expressing different enzyme variants into droplets. Each droplet becomes an isolated microreactor containing one cell and one enzyme variant. After some incubation to allow protein expression, you use Pico-Injection to add a lysis buffer. This breaks open the cells and releases the enzymes into the droplet volume. A second injection adds the enzyme substrate. Now each droplet contains enzyme and substrate. As the droplets flow through delay channels, the reaction proceeds. You can measure fluorescence at multiple points to get kinetic data. Finally, a third injection adds a stop reagent to quench the reaction. This lets you measure the endpoint accurately without ongoing reaction during detection. An important question arises. After you inject reagent or fuse droplets, how quickly does mixing occur? Does the reagent just sit there, or does it rapidly spread throughout the droplet? The answer is that mixing in moving droplets is surprisingly fast. As droplets flow through channels, they experience shear forces that create internal circulation patterns. These circulation flows rapidly mix the contents. The mixing timescales, as droplet radius squared, divided by an effective diffusion coefficient that includes both molecular diffusion and advective mixing from circulation. For typical droplet sizes of 50 to 100 micrometers, mixing times are on the order of 10 to 100 milliseconds. This is very fast, ensuring homogeneous conditions shortly after injection or fusion. Let's talk about practical design considerations. What do you need to think about when building a Pico-Injection or fusion system? First, channel dimensions must match your droplet sizes. For Pico-Injection, the main channel should be slightly wider than the droplets to allow smooth flow. For fusion, the fusion chamber geometry determines whether droplets pair correctly. Surfactant choice is critical. You need surfactants that stabilize droplets during storage and flow, but they shouldn't prevent fusion when you want it to happen. This often requires careful optimization and sometimes custom surfactant molecules. The viscosity of your oil phase affects flow stability and droplet behavior. Higher viscosity oils provide more stable droplets, but require higher pressures to flow. You need to balance stability against practicality. For Pico-Injection, you need reliable droplet detection and fast response times. Many systems use laser-induced fluorescence to detect droplets, then trigger injection with microsecond precision. Let's calculate the throughput you can achieve with these systems. How many droplets can you process per hour? And what does this mean for experimental capacity? A typical high-performance system might generate and process 100 droplets per second. This is limited by droplet generation stability and detection capabilities. At 100 droplets per second, you process 360,000 droplets per hour. This is an enormous throughput compared to conventional well-plate experiments. Running continuously for 24 hours gives you about 8.6 million droplets per day. If each droplet is an independent experiment, this represents massive parallelization. One of the most powerful aspects of these techniques is temporal control. By carefully designing your channel layout and injection points, you can create precise reaction timing. Here's an example of temporal control. The first injection happens at time 0. By designing the channel length and flow rate, the second injection occurs exactly 5 seconds later. A third injection happens at 12 seconds. Each droplet experiences the exact same time sequence. The channel length between injections equals flow velocity times desired time delay. This simple relationship gives you precise temporal programming. A practical question: what about reagent stability? If you have a reservoir of reagent sitting in your injection channel, does it degrade over time? This is a real concern for sensitive reagents like enzymes or cells. Best practices include minimizing dead volumes in injection channels, using cooled reservoirs for temperature-sensitive reagents, and replenishing reagent stocks regularly during long experiments. An alternative approach is to generate reagent droplets on demand rather than storing bulk reagent. This keeps reagents in isolated, stable droplets until the moment they're needed for fusion. Let me describe a real-world application that showcases the power of these techniques. High-throughput drug screening. Imagine you want to screen 10,000 compounds against a cancer cell line. Traditional well-plate methods would require expensive reagents and considerable time. Using Droplet Microfluidics, you encapsulate small numbers of cancer cells in droplets. You inject different drug compounds into different droplets. After incubation, you inject viability dyes and measure fluorescence. A typical well uses 1 microliter of reagent. Each droplet uses 50 picoliters. That's a 20,000-fold reduction in reagent consumption. For expensive compounds or rare samples, this is transformative. One technical challenge worth discussing is cross-contamination. In Pico-Injection systems, can material from one droplet contaminate the next? There's a risk that after injecting into one droplet, some reagent remains in the injection nozzle and gets carried over to the next droplet. This would compromise the independence of each droplet experiment. Solutions include wash cycles between injections, using positive displacement pumps that completely clear the injection line, and designing nozzles with minimal dead volume. With proper design, carryover can be kept below 0.1%, which is acceptable for most applications. Let me mention some exciting emerging developments in this field that go beyond basic Pico-Injection and fusion. Modern systems can sort droplets based on fluorescence or other properties, then selectively inject only into droplets that meet certain criteria. This creates feedback loops, where previous results guide subsequent additions. Some advanced devices have multiple injection sites in series, each capable of adding different reagents. This enables complex multi-step protocols with 5 or more sequential additions. Rather than storing pre-mixed reagents, some systems generate reagents on chip by mixing concentrated stocks in precise ratios just before injection. This provides even more flexibility and reduces waste. Let me share some practical tips that will help you succeed if you're setting up these experiments yours. If you're new to Droplet Microfluidics, start with passive fusion. It's more forgiving and doesn't require fast electronics. Once you master fusion, move on to Pico-Injection. Surfactant concentration dramatically affects droplet stability and fusion behavior. Spend time optimizing this parameter. Too little surfactant causes coalescence. Too much prevents desired fusion. Always use high-speed imaging to validate that injections or fusions are happening as expected. What looks good at low frame rates might show problems at high speed. Flow rates can drift over hours due to evaporation or pressure changes. Characterize your system's stability and implement feedback control if needed for experiments lasting more than an hour. Let me summarize the key principles we've covered about Pico-Injection and droplet fusion. Both Pico-Injection and droplet fusion solve the fundamental problem of adding reagents to isolated droplets in flow. Pico-Injection relies on timed pressure pulses that inject femtoliter to picoliter volumes through narrow nozzles. Droplet fusion creates separate streams of sample and reagent droplets that merge in a fusion chamber. These techniques enable complex multi-step reactions where timing and sequence are precisely controlled by channel geometry and flow rates. Applications range from enzyme kinetics and drug screening to material synthesis and single-cell analysis. Looking to the future, these techniques will become even more powerful and accessible. Integration with machine learning will enable adaptive experiments where algorithms analyze droplet measurements in real time and adjust subsequent injections to optimize for desired outcomes. Continued miniaturization and cost reduction will make these tools accessible to more laboratories. We're moving toward disposable chips and simplified control systems. Combining droplet microfluidics with analytical techniques like mass spectrometry will enable new types of chemical and biological analysis at unprecedented throughput and sensitivity.